So now we're ready to report the internal forces that are found inside this beam. So more information about those is going to be found in that node right there. If you want to link to it, that'll tell you more about internal forces. So right now I've redrawn the solved free body diagram, and we have no loads in the axial direction. So that will mean that the internal axial force is equal to 0. So that diagram is not included here. And so what we're going to do is move left to right across the beam. And as we encounter different loads, our shear diagram is going to change. So as I think of this thing as moving in the positive x direction, as we first get onto the beam, we encounter a 417 pound load that's going down. Now the fact that that was a support force, right, the beam really knows no difference here between that and an applied load. And all we have are loads on the beam, and so that's going to kick my shear diagram down. We will derive that shortly, just on the next page, but a load in the down direction is going to move my shear diagram down. And so then I continue moving across the beam, and the relationship between load and shear is that dV dx is equal to negative W, where W is the distributed load on the beam. Again, this is all highlighted back in node 3. And so we have no distributed load on the beam over the next 6 feet. So down here on the shear diagram, we end up with a flat line. So the line stays at 417. Then at point B, we run into a 500 pound load again going down. That's going to kick me down a total of 500, taking me down to minus 917. I then continue flat again between B and C because I have no distributed load on the beam. And then I encounter a point load at C of 1717. So that means the jump up. So that distance right there, using, again, the force axes, is going to be 1717. So I move from minus 917 all the way up to 800. That remains flat again. And at 800, I then kick back down to 0. So let's go ahead and work from our shear diagram to our moment diagram. And so we've got a couple of values that we're going to want to find here. In the shear diagram, right, we're going to find areas. So the first area is going to be the rectangle between A and B. And I'm going to call that one, labeled right there, A1. So A1 is going to have an area of minus 417 times 6 feet, giving me a total of minus 2502. I'm also going to need A2 right there. And A2 is going to have a much bigger value, bigger in the negative sense. Going to be from minus 917, as you can see, minus 917 times 6 feet. And lastly, I'm going to have A3. A3 would have an area which is positive of 8,000. All right, so the relationship between shear and moment tells us that the change in moment between any 2 points is going to be equal to the area underneath the shear diagram. So let's just deal with our first 2 points here, point A and point B. And so the equation is going to say that MB minus MA has to equal the area underneath the shear diagram between A and B, which for us would be A1. And so we've already found A1, which was equal to minus 2502. And so we have an equation that says that MB minus MA is equal to minus 2502. And we also know that MA is equal to 0. And we're going to solve for the moment at A shortly. The moment at A is equal to 0 because it's a free end and there's no applied moment. And so the moment inside the beam is going to be 0. So that then gives us an opportunity to solve for the moment at B. Next, we would move from B to C with the exact same relationship. that would tell us that the moment at C minus the moment at B is going to be equal to A2, the area underneath the shear diagram between those 2 points. And so we've got values that we can plug in. I can take MB from above. That thing goes right there. I've got A2 from my previous calculation. And then I can solve for MC. And the way I'm going to connect those points is with a straight line. Right? The other relationship we know is that dm dx is equal to v. That says that the slope of the moment diagram is equal to the value of the shear. So if the shear diagram is constant, then the slope is going to be constant. So all the lines over here on my moment diagram are going to be straight. So again, here's my MB. There would be MC. All right, I know MA is equal to 0. And then to close this thing, we want to use point D. So then the moment at D minus the moment at C is equal to A3. So we just plug in the values that we have, solve for as we've moved along. We know MC now. We've got A3 from up above right there equal to 8,000. And that gives us now a closing value of MD, which should be exactly 0. It's not, but is it close enough? And from a percentage error point of view, we would just be comparing 4 to some of the other values, perhaps 5,000. And that is going to be small, especially in a percentage difference. And so our very last piece here would then be to draw a deflected shape. Right, the deflected shape is going to have to obey all the boundary conditions. I've got a pin and a roller, so in the transverse direction, I know that I'm going to have 0 deflection and also V equals 0 at the roller. Throughout the whole beam, I have an unhappy face, so I need to draw something that has unhappiness throughout. And so to do that, I need to start with a positive slope, which would then give me the ability to go reach through point C, which is the roller, and continue on a negative, with a negative curvature all the way to the end of the beam.